Log on, tune in, find out. Another good idea from Cambridge.
Rudelson, and he will speak about row products of random matrices.
Thank you very much. First, I'd like to thank the organizers for inviting me here. And I'm going to talk about large random matrices and their spectral and geometric properties, in particular about singular values. If we have, say, an matrix A and n is greater than n, then the singular values are just the eigenvalues of the matrix A transpose A, which I arranged in the non-increasing order. And the first singular value is the norm of the matrix A considered as a linear operator from Rn small to Rn capital, or the maximum over the sphere of the norm of Ax Euclidean. And the last singular value is the minimum of the same quantity. If
you say the eigenvalue is 80A, you mean square root of 80?
Sorry, square root of 80, of course. And in the case where when the entries of A are independent and identically distributed, the behavior of these extreme singular values are well understood, in particular if n is greater than, say, 1 plus epsilon n, then both the biggest and the smallest singular values are of the order square root of n capital. So C1 square root of n is less or equal than Sn of A less or equal than S1 of A less or equal than C2 square root of n if the entries are independent, identically distributed, and C1 and C2 may depend on epsilon. They are actually, C1 will actually depend on epsilon, and the dependence is known. So this case is very well understood, and I'm going to consider the case where the columns of A are independent and the rows are not. So the first question would be, why would one bother with such situation? And we'll consider a concrete case of such dependence. And the answer is twofold. First, this appears in real problems, and second, the construction we are going to consider exhibits some phenomena which cannot be observed in the IID situation. So let's define what we mean by the row product. First, let's consider two vectors x and y in Rn and define x, the product of x and y, as just coordinate-wise product. then assume that we have two matrices with the same number of columns, and B m by n and then define the row product B matrix with rows A J B K, where A, J, and B, K are rows A and B. So I take two matrices with the same number of rows, of columns, sorry, and I take any two rows and then the row of the product is the entry-wise product of these rows. Have a bigger matrix. And if this one has n rows, this m rows, then we'll have n times m rows. And of course, this definition depends on the order of in which I enumerate the rows of the row product. But if we consider spectral properties or geometric properties, then the order of the rows wouldn't matter, so you can take any order what you like. So why would such structure be interesting? It appeared in several contexts. One of them, it is related to the implementation of Johnson-Lindenstrauss lemma. Suppose that we have many points in Rn, so x1, etc., x m in Rn, and we want to reduce the dimension without distorting the structure of this set, which means that the distances between any 2 points in this set will be approximately the same after we reduce the dimension. The easiest way to reduce the dimension is a random projection, and that was precisely what Johnson and Lindenstrauss used. We showed that if P is random projection and the rank of P is greater than C log m, then with high probability the distance between the projections of 2 points will be approximately the same up to the scaling factor, and the scaling factor is the square root of n over rank p. It will be between 1 minus epsilon and 1 minus epsilon times the norm of x j minus xk and 1 plus epsilon times the norm of xj minus xk for any pair of the points from this set, and this constant would depend on epsilon. Again, the random projection, which can be implemented as a matrix with ID entries, solves the problem perfectly. However, it is rather costly to implement. You have to introduce n times the rank of the independent random variables. So the other approach would be to take a random coordinate projection. Suppose that you choose some coordinate system in Rn, and then you project every 2 points on a random coordinate subspace, and then you can hope that with high probability the shrinking factor, the distance shrinks by the same factor as for the random projection, and it works perfectly fine if the coordinates of xj minus xk are commensurate. For example, if xj minus xk has coordinates like 1, etc., 1, then a coordinate projection with respect to the standard coordinate system would just erase part of these ones, so the norm would change exactly by the shrinking factor, square root of n over the square root of the rank. However, there are problematic directions. If I consider the direction, the coordinate direction 1, 0, etc., 0, then if I take a random projection, I can miss this one, and the norm remains 1. It doesn't shrink at all. Or a random projection would cover the kernel of the random coordinate projection will contain the first basic vector, and then the projection will be just 0. Again, a big distortion. So this construction works for most points, but if we don't know the configuration in advance, and this is the real situation, we cannot use it. So a few years ago, Ailon and Chazelle proposed to mix the two approaches. Namely, you take a coordinate system, and a coordinate system is in Rn is given by an orthogonal matrix, and then you consider a random coordinate projection, which is a submatrix of a coordinate of the orthogonal matrix. So A is a submatrix of an orthogonal matrix. This has no chance to work, but then one can do the following. We take this A and multiply the columns of A by independent random signs. So here I use epsilon 1, epsilon A, say M, 1, epsilon 1, so I use epsilon 2, A, M, 2, epsilon 2, etc. And epsilon. In other words, you consider the row product A times epsilon, where epsilon is epsilon 1, etc. Epsilon n, a random vector of signs. And it was found, discovered by Alon and Chazelle, and later much improved by Alon and Liberty, that this matrix is in a sense much more random than a random submatrix of an orthogonal matrix. Namely, it works fine as a Johnson-Lindenstrauss type of projection. And instead of one vector of signs, you can take the same submatrix and multiply it by several different vectors of signs, and then you have a product of A times, say, delta, where delta is a random matrix of signs with a few rows. Another source of this row product is another computer science problem, namely the privacy protection problem. Here, assume that D be D by n 0, 1 matrix, which is a database. So D has D rows which correspond to D different attributes, and n columns which are n individual records. And we want to release the summary data on this database without compromising the privacy. So the standard way to release the summary data is, which is actually used in statistics, is to publish contingency tables. So what is the contingency table? We take a small number k, small compared to the dimensions of this matrix, which are huge, and then we publish the number of, we take any set, so we take any set J in the set of attributes of k elements, and we publish the percentage of the records which have all attributes from the set J. So if my k is 3, so I'm looking at all columns containing 3 ones in certain rows. So this will be my set J, and then I count the number of entries which contain 1 in all these positions, and then we publish a vector x in R D choose k, the vector of all these percentages. This vector is called the contingency table. Okay. Now suppose that the adversary knows a part of the database, it is leaked, or it is publicly available. The last case is quite real. All the known privacy breaches were based on cross-searching on different databases, where you take a publicly available database and use its entries to recover the entries of a secret database. So suppose that we have a database which consists of a few publicly available attributes and a few secret attributes. So D prime is available. And then we publish a contingency table. Let's consider some of the entries of this contingency table. I'll take k-1 attributes from the matrix D prime, and 1 attribute will be from the secret part. So first, what is this vector x, the contingency table? I can represent this x as we stated that we need ones in all specified places, and we can say that the product of these entries will be 1. So in this I can write this x as a product of D, row product of D with itself, k times and then I calculate the percentage of non-zero entries. To do it, I multiply it by the vector w, where w is the vector of all ones. Okay. Now, if part of the database is available, then this big vector x will contain among its coordinates a smaller vector. Let's call the secret part y, or not to mix it with x. So this vector will contain, if y is row of y, then x contains all coordinates of d prime times d prime times etc. times d prime, Here I need k minus 1 times and times y times w. But this can be rewritten as the same d prime times etc. times d prime, the row product, and the usual multiplication by the vector w. Okay. And this matrix, if we know d prime, can be calculated. And the contingency table, this vector x is released, so we know this product, we know the matrix, and we have a linear system. If I call this matrix, say d tilde y equals some x tilde, this is known and this is known. So if the number of available attributes is big enough, we can reconstruct a secret vector y just by solving linear system. And then we can repeat it for all entries of y, so we recover the secret part completely. This depends, of course, on the properties of d tilde. If and what we need is that d tilde will have the left inverse. Now, to avoid this, one doesn't release the contingency table precisely, but releases it with some noise. So instead of this, we write d tilde y is x tilde plus x noise and then if we multiply it by the left inverse, so let L be the left inverse d tilde, and then what we can recover is dy is x tilde, but what we know is x tilde plus x, the noisy part, and if we apply the left inverse to it, we'll have L of x tilde plus xn. This we can calculate. So what is the error of that we commit when we or the adversary tries to recover the secret vector? This error will be less or equal than the norm of the left inverse times the noisy part, the norm of the noisy part. And if the norm of the left inverse is small, this error will be small. And then if we know, and we know that all coordinates of y are zeros or ones, we can recover almost every coordinate just by rounding. If this is, say, O small of the square root of n, then most of the coordinates of y can be recovered from the coordinates of this vector, which we can calculate just by rounding. So the norm of L would give us the lower bound of the number of noise that we have to add. And the norm of L, the norm of the left inverse, it's easy to see, will be precisely the smallest, the reciprocal of the smallest singular value of the matrix d tilde. So whenever we have the smallest singular value of the row product, we get the bound of the necessary noise we have to add. So this is the name of the game. We want to study the row product of matrices, and we want to find the biggest and the smallest singular values. One thing is clear, where the row product, if I take any random matrices, so let delta 1, etc., delta k be any matrix, in particular random matrices, then if I form a row product of these matrices, the entries of this row product will this will be a submatrix of the tensor product. And the spectrum of the tensor product is well understood. So we can try to use this. But it turns out that the spectra of these two matrices have very little in common. For example, for the tensor product, the first singular value for the random case is just the sum of the square. If I take the dimensions, say d by n, this will be the sum of the square roots of the dimensions raised to the power k. And the least singular value will be of the order of the difference. For the row product, the picture which can be seen in computer experiments is different, and say let's consider n less than d to the power k, even much less than d to the power k, and then, at least for two matrices, what was obtained on computer experiments, that the row product has the largest singular value about d, and the smallest singular value is about D as well. So it's a nice embedding, and if you compare this to other types of random matrices, this is the picture that you get for random matrix with independent identically distributed entries, because D here for k equals 2, D is the square root of the number of the rows. Each one has D rows, the product has D squared rows. So this is the square root of the number of the rows.
So your point is that this is true for a much larger n than for the tensor product.
Right. Right. If you okay. So after this was noticed, try to prove it in general, and it turns out to be true in general. So from the point of view of the biggest and the smallest singular values, the behavior of this row product is the same as the behavior of a random matrix with independent, identically distributed entries, regardless of the fact that the entries of this matrix are obviously dependent. More precisely, so let first let n be less or equal than d to the k, and let delta 1, etc., delta k be d by n matrices with independent centered entries and we have to add some conditions like the variances are uniformly bounded below, and then the biggest singular value of delta 1 times etc. times delta k is greater than a constant times the square root of the number of the rows, which is d to the k over 2, is less or equal than c minus c d. So, the typical value of the first singular value is the square root of the number of the rows. And second, if n is much less than d to the k, and I'll write more precisely in a second, then with the probability that the last singular value is smaller than the same, what we expect here, c prime d to the k over 2 is also exponentially small. Here, however, I cannot get to the proportion of d to the k. It is slightly weaker, and this is a constant over the log q of d, where the log q is an iterated logarithm. So if I know the log q d is the log etc. log d q times. Okay, and of course in this case this constant c prime will depend on q, but it will be independent of the dimensions of the matrices and the nature of random variables. So from one side, the first and the last singular values are more or less the same as for the matrices with independent random entries. From the other side, these probabilities are small, but they are not as small as for independent entries, where we must have the exponential of the number of rows, which is d to the k. Here we have only d. And this looks like a technical nuisance, but actually it leads to the rather interesting phenomenon. And here let's consider another application of random matrices. If we have a random matrix A, which I consider an operator from R n small into R n capital, then and n capital is, say, greater than 2n small, then with high probability for any x in Rn, the norm of Ax in L1 will be proportional to the norm of it in L2. So there are two constants, small 2 less or equal than 1 over square root of n norm Ax in L1 less or equal than C prime Ax in L2, which means that this matrix provides a roughly Euclidean section of the cross polytopes, of the cross polytope with high probability. And actually, the structure of the cross polytope has nothing to do with it. We can replace this one by any Banach space norm if the norm satisfies a certain condition, and this condition is on the volume of the unit ball of this space. So we can write the norm of AX. Instead of this, we can write the norm of AX D, and if we have a body D such that first the Euclidean ball of dimension n capital is contained in D, and second, the ratio of the volumes of D and the Euclidean ball root is bounded. This happens, of course, for the scaled cross polytope. But there are many other bodies which contain Euclidean ball and have roughly the same volume. And if the matrix has independent random entries, the same proof works, and the same proof gives that the norm with respect to this body D will be equivalent to the Euclidean norm. And this leads to the question, what happens to the row products? They are less random, as we see these bounds are optimal in D. They are less random in a sense than the matrices with independent entries. And it turns out that this volume ratio property fails completely for the row products. So indeed, this problem with little randomness manifests itself in the fact that the volume ratio property doesn't hold for them.
You mean the volume ratio isn't enough to make that?
Right, right. It is not enough, and one can construct a body D and random matrices delta 1, etc., delta k, so that this wouldn't happen with probability 1.
But you don't know it for L1? For L1 it's
that's the point. So for this purpose, the row products look hopeless, but yet, surprisingly, for L1 everything works. And precisely f delta 1, etc., delta k d by n random matrices independent entries, then and n satisfies the same condition, c over the log q d to the k. So it's almost proportional to the number of rows but not quite. The coefficient depends on the dimension, but very little. Then, with probability at least, again, 1 minus c e to the negative cd for any x in Rn, the L1 norm of delta tilde times x scaled by 1 over square root of the number of rows, which is d to the k over 2, is between one constant L2 norm and another constant L2 norm, where this d tilde is the row product. So this Gaussian section property still holds, but the reason for it is different. It's not the volumetric consideration. You have to use something else. And the problems the major problems which arise in proving all these results is exactly this wrong exponent, which, as I said, is optimal. So, for example, the first singular value is the norm of the matrix, and we know how an easy way to estimate the norm of the matrix. We take a discretization of the unit sphere. We choose, say, a 1/2 net, and then the norm of the matrix doesn't exceed twice the supremum of the norm of AX over 1/2 net. So we take any element of 1/2 net, consider the norm of AX, and it usually has very good tail behavior. We can use some large deviation inequality and show that this norm cannot be large with any significant probability. Then we just multiply this estimate by the cardinality of the net. If we try anything of this type here, it would fail miserably, because we cannot get a tail estimate better than exponential of d. Yet the cardinality of a 1/2 net in the range space is exponential in d to the k, so there is no hope that the union bound will apply. Okay. For the least singular value, the situation is even worse, because if we consider the small ball probability, the probability that the norm of delta tilde x is less or equal than something, this would depend very significantly on the direction of x, and we cannot obtain a uniform bound on this small ball probability. So this would depend on x, and this will depend on the direction of x. We cannot obtain a uniform bound for the probability. This case was already encountered before, and the usual treatment was to introduce several epsilon nets for different parts of the sphere and then combine this. However, this approach doesn't work either. Actually, it works, but it leads to accumulation of parasitic logarithms, and one cannot get the same quantities for the first and the last singular values with this approach. What is done instead is some kind of a chaining argument. I cannot discuss it in details, but chaining is a standard way to obtain the estimate for the supremum of a random process. Here the problem is significantly different. We have to estimate the infimum of a random process, and yet there is a rather easy chaining argument which can do this. I think I am running out of time, so I'll stop here.
So are there known results in distribution for Gaussian matrices?
For distribution,
Well, or more precise.
no, this I think this is quite doable, because for distribution the moment methods are available, and this is this row product situation can be quite easily analyzed with moment method.
And there is no way to relate a general thing to Gaussian, or say sub-Gaussian to Gaussian? Or?
No, for sub-Gaussian, I don't know it, and probably not. Actually, I don't think so, because if you take sub-Gaussian matrices, the tail is nice. If you take a row product, you multiply several sub-Gaussian variables, you get what is called psi alpha for alpha less than 1.
But this is true also for Gaussians. When you multiply Gaussians, you also.
Right. But the question of Frank was about the distribution function for the individual singular values.
Questions? So if not, let's thank the speaker again.